Okay, so last time we talked about the following map from R2 to R2, which is given by f of xy equals x minus y comma x plus y, and we noticed the following fact that it does the following to a square of side 1, it maps it to again a square, but of a larger side length square root 2 and also rotated by an angle of 45 degrees. So, this is the image of this unit square under this map. Okay, so, this point is 1 comma 1. So, this is in fact a side of a square of side root 2 and which in fact makes an angle of 45 degrees with the x axis. We call it pi by 4. Okay, so, we therefore said that it seems like there are two operations happening here at once. So, this is the natural notion of composition of maps. So, recall what did composition mean of functions. Suppose I have functions, let us call it g1 is a function from R2 to R2 and I have another function g2 from R2 to R2. So, all these are R2. Then their composition, so let us call it g2 composition g1. So, let us define H to be g2 composition g1. So, what is this? This is the following map is a map is the map which is defined by. So, firstly where is it a map from? It is again a map from R2 to R2. And what does it do? It takes a point x comma y on the plane and sends it to, so it is g2 composition g1. So, it is g2 evaluated at whatever g1 does to x comma y, right. So, this is the usual notion of composition. You follow one map up by the second one. So, this is another way of saying it. So, you apply g1 first and then you apply g2, right. So, if you do first g1 and then g2. So, this is sort of what we meant last time by saying that map f that we looked at seemed to be doing two things at once. What it really was doing two things one after the other. So, let us see what what I want to do next is to try and express this map f as a composition of two simpler maps or two more familiar maps that we have already looked at. So, for that purpose let us actually define these two maps. So, I want to take specific examples of g1 and g2. Let me define g1 to be the following map. It is x minus y divided by square root 2 comma x plus y divided by square root 2. Okay, so, that is g1 and g2, sorry that is g1, and g2 of xy I define it to be just square root 2x times square root 2y. Okay. So, I am taking two particular examples of g1 and g2, one of them given by the first formula, the second given by the second formula. So, observe that g2 is something that we have already looked at, it is just the uniform dilation by a factor of square root of 2. So, g2 of course is familiar, this is just the dilation or a uniform dilation by square root 2. So, everything gets expanded by square root 2. So, we will return to g1, but first observe what is the composition of these two maps. So, suppose we did g2 composition g1. So, let us call H as g2 composition g1 and see what this map H is. By definition it is g2 of g1 of xy. So, let us evaluate g1 first. g1 is x minus y by root 2, x plus y by root 2. That is what g1 does, and g2 simply multiplies each factor by root 2. So, this then gives you x minus y comma x plus y. Okay. So, in other words what is this? Well, this is the original function f that we started out with. So, this is exactly the function f. So, what this means of course is that the original function f is rather it really is a composition of two simpler functions. It is G2 composition G1. Now, let us try and understand G1 better. G2 of course we have now understood, so it is a dilation. Now, what does G1 really do? Okay, so that is the only remaining part of the puzzle right now. Okay, so the only question that remains here is to understand what G1 is. Now, let us start out with the formula. G1 of x comma y is just x minus y by square root 2 comma x plus y divided by square root 2. But to understand it more geometrically, let us do the following. Let us take a point x y on the plane. Let us say imagine it is at a distance r from the origin, and which makes an angle theta with the x axis. So, we have the following trigonometric relations, that x is just r cosine theta, y is r sine theta, and now we apply G1 to the point x y. So, by the formula this is just x minus y by square root 2 comma x plus y. So, x is now r cos theta plus y by square root of 2. Now, let us do the following. Let us analyze each of these. Remember, 1 by square root 2 that appears in this formula can actually be thought of as the following. It is cosine of 45 degrees, it is cosine of pi by 4, or in fact the same as sine of pi by 4. Okay, so, cosine and sine of 45 degrees are both just 1 by square root 2. So, what we can now do is to rewrite the x coordinate. So, what did we have? We had r cos theta by root 2 minus r sine theta by root 2 as the following. It is really r times cosine of theta cosine of pi by 4 minus sine of theta sine of pi by 4, and this is just r. So, now we use the trigonometric identity for the cosine of a sum. So, cosine of theta plus pi by 4 would exactly be cosine theta cosine pi by 4 minus sine theta sine pi by 4. So, in fact what this tells us is that if you take G1 of x y, if you look at G1 of the point x comma y, what it is mapping to is a point x dash comma y dash, which is given by the following. The x coordinate of the new point is just r cos theta plus pi by 4, and if you sort of work out the y coordinate similarly, you will find that it is just r sine theta plus pi by 4. Okay, again you will need to use the addition formula for sine. So, what does this mean? Geometrically it says that the original point, which was at an angle theta from the origin and at a distance r, has now been mapped to, well, this new point is still at a distance r, but the angle is theta plus pi by 4, right. So, this is the original point x y has now been mapped to, well, a point here. So, it is just moved like this by an angle of 45 degrees. The length remains unchanged. In other words, this is just a rotation by 45 degrees. So, therefore, what is we have managed to answer the original question. G1 in fact is nothing but is the rotation by G1 is just the rotation by 45 degrees anticlockwise. Okay. So, finally, coming back to our analysis of f, remember f was just the composition of these two maps. So, recall that this function that we started out with is just the composition G2 composition G1. So, in other words, the function f that we looked at is just the following. You first perform a rotation by 45 degrees and then follow it up with a dilation by a factor of square root 2. Okay. So, that simple looking formula that we wrote out for the function f, it is just x minus y comma x plus y, but if you really analyze a little deeper, you find that the function f can be broken down into two simpler constituents, one being a rotation by 45 degrees and the other being just a simple dilation. Okay. So, what does this tell us? Well, it tells us lots of things because we know many properties of rotations and dilations. So, here is a consequence. Observe, this means that f preserves angles. If I have say two lines which make some angle theta and I apply f to it, what I will get will be two more lines which still make the same angle theta. And why is that? Because the first operation, rotation, does not change angles. The second operation, dilation, as we just saw, also does not change angles. So, when you do the first followed by the second, the angle cannot change, neither of the two constituent pieces can change the angle. Okay. So, f does preserve angles. What does f do to lengths? F dilates lengths by a factor of root 2. So, lengths are multiplied by a factor of root 2. Again, why is that? Because, well, a rotation does nothing to lengths, it preserves lengths, keeps lengths the same, whereas then when you follow it up with the dilation, the length will become multiplied by square root. And of course, areas. So, when lengths get multiplied by square root 2, you sort of expect the areas to get multiplied by a factor of 2. Okay. So, that is what happens in this case, that the areas do get multiplied by a factor of 2. Okay. So, what this tells us is often the simpler sorts of transformations we talked about, dilations or inhomogeneous dilations, rotations, translations, things like that, are often very good building blocks with which you can try and understand somewhat more complicated transformations of the plane. Okay. So, now one final example. Let's take the function f of x y defined to be x squared comma y squared. Okay. So, this formula is now again simple in a sense, but fundamentally different from all the examples we have looked at until now. So, observe, everything we have done until now has never had squares of the variable occurring in these two places. You have always had something which looks like some multiple of x plus some multiple of y, for instance, or some multiple of x plus a constant. So, what we have had so far have always been linear polynomials, if you wish, in the variables x and y in the first component and in the second component, whereas here the first time we see a square appearing. Okay. So, point to note here is that this is fundamentally different from all the examples so far. So, this is certainly very different. So, I should say this is fundamentally different from all preceding examples of transformations. And we will soon see this difference being expressed. So, for instance, here is the first thing, let us try and figure out what this map does to lines. Okay, that has often been our first step in all these prior examples. So, let us take a line. So, I am going to pick the line y equals x plus 1, it has slope 1 and a y intercept of 1. So, here is my line L, and let us see what this function f does to this line L. Okay, what sort of thing do you get on the other side? Okay, so, what's the approach? Let us write, just as we did earlier, we will try and write an equation for the image. So, let us call x prime y prime to be the image, let us call it f of x y. In other words, this is x squared y squared. Okay. So, x prime is x squared. So, this just means of course that x prime is x squared and y prime is y squared. So, now what we know is that the variables x and y are connected by an equation, right. When they vary, when x and y vary, they vary in such a way that y is always equal to x plus 1. This is the equation that we know. and what we now want to derive from here is an equation which tells you how x prime and y prime are connected, right, how do they vary is the question. So, let us try and figure out what this implies in terms of want an equation in terms of x prime and y prime, okay. And so of course that is equation for x prime y prime. So, it is again easy just like we did earlier. So, we will just rewrite y as the square root of y prime, y prime is y squared. So, it is square root of y prime equals the square root of x prime plus 1. Okay. So, imagine, so this is really the equation that you have which connects the variables y prime and x prime. Observe here y prime and x prime, since they are squares of these variables, are definitely positive. So, observe that x prime and y prime are definitely greater than or equal to 0. Okay. So, here is the equation that tells you how y prime and x prime vary. So, the best way to do this, of course, to square both sides. We will see what that gives us. So, it tells you y prime equals x prime square root of x prime plus 1 squared. So, that is this plus 1 plus 2 root x prime. Okay. So, that is the equation which tells you what, how y prime and x prime vary, and observe this is clearly not the equation of a line, okay, because of this factor here you have the 2 root x prime. This is clearly not the equation of a line. Okay. So, what this really implies is the original line that we had, y equals x plus 1, okay, that is the line L. When you map it under this function f, what it transforms to, what it deforms to is something very different, it is some curve now. Okay. So, y prime and x prime are both positive and they are connected by this equation, y prime equals x prime plus 1. So, observe if you only had the first two terms, of course, that is the same line, y equals x plus 1, but there is this additional term there. So, if you sort of draw it, it probably looks something like that. So, that is the curve. Okay. So, this is the curve which is the image of the line L. Okay. This curve is the image of the line L under this map F. Okay. So, the very first point here is that it does not map lines to lines. So, that is already a very fundamental difference, which means it actually makes life somewhat harder for us, because you no longer can figure out what happens to polygonal regions just by figuring out what happens to just the endpoints, just the vertices alone, because the line connecting those 2 points could have deformed to some funny curve connecting the vertices. Okay. But never mind. So, let us look at one further region. So, let us look at the circle of radius 1. So, I want to take circle of radius 1 and figure out what happens to that under this map F. So, my question now is, what is the image of the circle under this particular map F? Okay. So, let us try and do the same thing. Now, the circle again is a curve that is given by the following equation. It is all points x comma y on the plane which satisfy x squared plus y squared equals 1. Okay. So, that is the circle, and now again I will do the same thing. I will look at the image of this point x y, I will call it x prime y prime, and now, so what does that mean? X prime is x squared, y prime is y squared. And now the question is, can you now find an equation that tells you how x prime and y prime vary as x and y satisfy the given equation. So, observe that x prime is x squared, y prime is y squared, of course means the following as before, x prime and y prime are positive. But further, since the original 2 points lie on a circle, x squared plus y squared is 1. So, in other words, x prime plus y prime is actually 1. Okay. So, here is the conclusion about the point x prime y prime. As x comma y runs around the circle, the point x prime y prime, its image lies on well, it lies in the first quadrant because x and y are positive, but further it lies on a particular line, it lies on the line x plus y equals 1. So, here is the line x plus y equals 1, and this point x prime y prime must lie on this line, it can only vary on this line, that is what it implies. But further, remember, it lies only in the first quadrant. So, I do not even have the parts which are, it is not even a line anymore, it is only this particular line segment that it must lie on. Okay. So, let us look at the two endpoints. Here is the point 1 comma 0 and here is a point 0 comma 1, and you have the line segment joining those 2 points. What this transformation f must be doing is it must somehow map this entire circle just to that line segment alone. Okay. So, it is somewhat surprising at first glance. So, let us figure out what happens, how can a circle really just map to just a small line segment like this. So, imagine what happens here as x. So, let us look at the 4 parts of the circle, the 4 quadrants. So, here is the yellow portion, as x and y both live in the first quadrant, and let us say I move from this point here towards the point above, say I move like this along the circle. Let us see what happens to those points. So, this point here A, which is the point 1 comma 0, under this function f maps to, well, 1 comma 0, I square both components, I get this point. So, let me call it P and Q. So, when I move from A to B along my circle, A maps to P, B maps to Q under this map, and so what I get is I will move along this line or line segment from P towards Q. So, this is how the point moves when you move from A to B along the circle. Okay. Now, let us keep doing this. So, you move between, let us say, B and C. So, observe C is now the point minus 1 comma 0, and under this function f, C again maps to P because it is going to square both components. So, as you move from B to C, you will observe that all you are doing is just moving back down along this. So, you first move from P to Q and then you move back down to P. Okay. And well, it is similar, when you move from C to D, you move back up, and when you move from D to A, you move back down. So, you sort of do 4 iterations, you go up, you go down, you go up again, and then you go down finally. Okay. So, traversing the 4 quadrants of the circle amounts to, under this map f, what it does is it traverses this line segment up and down 4 times. And to really understand what this is doing, so if you also look at the region inside this circle, what it is going to do is just map it to this triangular region here. Okay. So, again something for you to check, it is an exercise, take points inside the circle, for instance the origin maps to the origin and so on. Now, what is the geometrical way of really understanding what this map does? Okay. So, after all of these various examples we are doing are with the following thing in mind, we want to get some geometrical intuition for how this function deforms the plane into other points of the plane. Okay. And to do that, we are really looking at certain sub-regions of the plane and figuring out what deformations they suffer under this function f. So, here is really what happens. So, let me just give you the description and leave it for you to convince yourself that this is in fact what it is. So, it is really the following step. You first take the circle. So, imagine I have a circular disc. So, a paper say which is in the shape of a circle, and imagine you have these 2 diameters. Now, you fold this circle. So, you really perform a fold, say along one diameter and then along the other, such that it is just a quadrant. Okay. So, there are 2 folds that you perform, first along the first diameter, it will make it a semicircle, and then along the other diameter to then make it into just a single quadrant. And now what you do is this quadrant under this function f, you sort of flatten out this circular arc into a triangular region. Okay. So, of course, the flattening is not, I mean that is just a geometrical term which just tells you that you are sort of doing something to that circular portion and making it a square. So, the exact thing is of course given by the formula x squared y squared, but what you are doing here is you are flattening this function f is now flattening this quadrant into a triangle. Okay, so finally that is the right angle triangle that you get joining the point 0 1 and 1 0. So it is really a two-step process here again. One, the circle is folded along the diameters into a single quadrant, and then this quadrant is flattened into a triangular region, and so this combined deformation is really what the function f achieves. Okay, so it does both in one stroke. Okay, so the key thing here is with this example at least the key point is to realize that this thing of lines mapping to lines that we keep talking about, or we kept talking about in all the earlier examples, is not something to be taken for granted. Okay, it is not always true that any given transformation may not map lines to lines. It can do some rather strange things to lines, make them other kinds of curves and so on, as we saw in this example. And so every time you have a transformation which you are trying to understand, it is important to check, for instance, that it does in fact transform lines to lines. If at all you want to see what is going to happen to triangles or squares or other polygonal regions, checking that lines map to lines is somehow the very first step. Okay, that is something that one must always do before one starts manipulating and playing with these functions a little bit more. Okay, so we will return to this theme of lines mapping to lines again. Specifically, next time we will talk about transformations which have that property that they map lines on the plane to lines on the plane. These are called affine linear transformations, and sort of special cases of those are what are called linear transformations. So these form a very important class of transformations which can be understood from many different points of view, and using other tools from other parts of mathematics, specifically things like matrices and so on. Okay, so the thing for next time is to try and understand these so called affine transformations and how matrices naturally make an appearance when you want to study affine transformations.